Chapter 2 is on vector spaces. In this chapter, we want to answer specifically in this chapter, we want to answer the following question. For AX equals B, is there one solution, no solution, or infinitely many solutions? Infinitely many solutions. So no solution, one solution, or infinitely many solutions. Hopefully by the end of this chapter, which is probably spread over 5 lectures, 4 to 5 lectures, we should know by looking at the matrix and doing some elementary operations whether the solution exists. If it exists, is it unique, or there are infinitely many solutions, or the solution does not exist. So the first section is on vector spaces and subspaces. By the third lecture, hopefully we'll see that with each matrix there are 4 associated subspaces, 2 belonging to Rm and 2 belonging to Rn, and in chapter 3 we'll see that the subspaces belonging to Rm are mutually orthogonal, and the subspaces belonging to Rn are also mutually orthogonal. So for that you have to wait until chapter 3, but by the end of the third lecture you should be able to figure out what the 4 subspaces are associated with any matrix. So what is Rn, Rm? So Rn is a space. Sometimes they write a fancy R like this. So Rn is a space of all column vectors with n components. So this n is over here with n components. This R specifies real. So for example, R1 is a line, R2 is the familiar xy plane, is the xy plane. Okay. Within all vector spaces, so vector space is normally written as a capital V. Within all vector spaces, it's not bold or italicized, it's just a simple V or W. Within everything in capital letters. Within all vector spaces, 2 operations are possible. 2 operations are possible. You can add, so first one is, can add 2 vectors, and can multiply vectors by scalars. All vectors by scalars. So the first one is actually vector addition. This is vector addition, and this one is scalar multiplication. Scalar multiplication, and we say, so what we are doing here is we are taking all linear combinations, taking all linear combinations. So simple way of writing first these two steps is a vector space is closed. Closed meaning when you add two vectors, the result is in the vector space, and when you multiply the vector by a scalar, then the result is still in the vector space. So you say the vector space is closed with respect to vector addition and scalar multiplication. Addition and multiplication follow these 8 rules. Addition and multiplication satisfy these 8 rules. Actually, there are only 2 or 3 that are important. Others are just the reiteration of the same thing. And what are these 8 rules? The first one is commutative law is true. So if you add x plus y, this is the same thing as adding y plus x. So addition is commutative. Addition is also associative. So x plus y plus z equals x plus y plus z. A unique vector 0 exists such that, so the inverted epsilon is actually such that x plus 0 equals 0 plus x for all x. This is for all. For each vector x, and this is also true. Why? Because in here, if my scalar is a 0, and obviously 0 is the origin is already is always in the vector space. For each vector x, there exists. So this is there exists a minus x such that x plus minus x is the 0 vector. And then 1 times x is x. C1, C2 are scalars. Multiplied by x is same as C1 into C2 into x. And distributive c into x plus y is equal to cx plus cy. And finally, c1 plus c2 into x is equal to c1x plus c2x. So a real vector space is a set of vectors together set of vectors together with rules, together with rules for vector addition and multiplication by scalars. Multiplication by scalars, or scalars by scalars which are real numbers, which are real numbers. Okay, so the resultant vectors, the resultant vector, which is the same thing as saying that the vector addition and scalar multiplication is closed. The vector space is closed with respect to scalar vector addition and scalar multiplication. The resultant vectors must satisfy the above 8 conditions. The above 8 conditions. So we are concerned with vector spaces. So we are concerned with vector spaces that are inside the standard space, Rn. For example, a plane in 3 dimensions, a plane in 3D passing through the origin the origin is always has to be included in the vector space, because C can always be taken as 0. Passing through the origin is also a vector space, and we know from chapter 1, a plane is infinitely long with zero thickness, is also a vector space. So what is the subspace? Space and subspace are related in the same manner as a subset and set are. So just the same relationship between a set and a subset holds in this case too, between a space and a subspace. So a subspace of a vector space is a non-empty subset, that satisfies the requirements for a vector space, that is linear combinations stay in subspace, for example, x plus y is in subspace and C times x is also in subspace. And what I've been telling you all along, 0 will belong to all subspaces, because, so an inverted therefore, so this is because because C equals 0. Okay. So the smallest subspace contains smallest possible subspace contains the zero vector because 0 plus 0 equals 0 and C times 0 equals 0. And the largest possible subspace is the entire space. The largest largest possible subspace is the entire space. Okay. So let me ask you a question. What if in 2 dimensions, so consider R2 such that x is greater equal to 0 and y is greater equal to 0, which simply means we are in the first quadrant, implies we are in the first quadrant. And we don't want to put them as vectors. Oh, it's all right. So if we are in the first quadrant, so we are over here. So y, x, this is the first quadrant. This is your 0. So is the first quadrant a subspace? So is first quadrant a subspace of R2? So this is the question. Is the first quadrant a subspace of R2? And it's not. It's no. Why? Because for a negative C, C times x may be in the third quadrant, maybe it's definitely in the third quadrant, because C times x is in the third quadrant. Okay, so what if we add, what about first and third quadrants? So do they make up a subspace, first and third quadrant? So this is the third quadrant. So if you have a vector over here, you have a vector over here. So obviously you can have a resultant. Which is not in either one. So obviously first and third quadrant together will also not make a subspace. So it's still not possible. So still not possible because some combination of vectors might end up in other quadrants. Okay, so this implies the smallest possible space, the smallest possible subspace containing first quadrant is the entire space R2. Okay. What about vector space of 3 by 3 matrices? Vector space of 3 by 3 matrices. I think we can also look at these 3 by 3 matrices as an array of 9 elements. So in any case, so one possible subspace is a set of lower triangular matrices, and I hope you know what are lower triangular matrices after the first chapter. And another possible subspace is a set of symmetric matrices. So in a symmetric matrix, the elements above and below the main diagonal are the same. In a lower triangular matrix, the elements below the main diagonal are non-zero, and above the main diagonal are zero. Okay. So let's look at the first subspace, that is the column space of matrix A. Column space of matrix A, and you call this as CA. Okay, fine. I'm not going to write column space of matrix A all the time. I'm just going to write C of A. So column space, and we saw from the first chapter that column space is simply a combination of columns. So whenever you post multiply a vector with a matrix, then you are actually taking, so when you're doing A times X, so A times X is simply combination of columns of A. This is simply a combination of columns of A. So when you post multiply here, it's a combination of column. When you pre-multiply here, it's a combination of rows. So here, if you multiply here, this is a combination of rows, and obviously we are going to be pre-multiplying not by, so this is a column vector, and this, by the way, is a row vector. So we'll see when we are discussing the last subspace, okay, we are actually pre-multiplying the matrix to get some result. So when you're doing A times X, you are actually looking at the combination of columns of A. So column space of A contains all linear combinations of columns of A. So try to remember this thing, or actually even if you don't remember, try to visualize this thing. Whenever you are writing, when you are writing A times X, A times X is simply the column space of A. Okay. And it is a subspace of, and this A is, by the way, m by n. So this A is m by n. So there are m rows. So A is m by n. So m rows, n columns. So there are m components. So implies m components in a column, and this implies n components in a row. Okay. So obviously, since there are m components, so this is a subspace of Rm. And let me give you an example. And probably will be using this example over and over again. So this is 1, 5, 2, 0, 4, 4, U, V, unknowns, equals sum B1, B2, B3. So remember, we want to answer the question whether Ax equal to B has a solution, one solution, no solution, or infinitely many solutions. So this is A, this is X, and this is B. Okay, so this is 3 by 2, this is 2 by 1, and obviously this is 3 by 1. Okay, so the question is, Does combinations of columns equals B? So the question is, does combination of columns equals B? We have more equations than unknowns. More equations than unknowns. So here the case is m is greater than n. So m is greater than n. And usually, usually we will not have a solution. Usually there will be no solution. Why? Because there are less unknowns and there are more equations, so it's unlikely that we satisfy everything. So usually there will be no solution, except in some cases. However, and I'll tell you when. However, the system will be solvable. The system will be solvable for a thin subset of all possible B's. And what does this mean? This simply means AX equals B is solvable. And this is what I want you to take from today's lecture. Take away from today's lecture is AX is equal to B is solvable if and only if. This one is if and only if. If and only if B can be expressed as a combination of columns of A, which simply means B lies in column space of A. So AX is equal to B is going to have a solution if B lies in the column space of A. That is all you want to. So whenever somebody asks you, okay, when will AX equal to B have a solution, the answer is this one. Whenever B lies in the column space of A. So let's look at this one. So we know from chapter 1, U will multiply the first column and V is going to multiply the second column. And if I do that, so U times 152 plus V times 044, this should be equal to B. So one possible B is U is equal to 1, V is equal to 0, which is the first column, implies B is equal to 152. Obviously, this lies in the column space. Or the other condition is U is equal to 0, V is equal to 1. This implies the second column, B is equal to 044, or linear combinations of U and B, or B is a linear combination of U and V. Otherwise, we will not have a solution. So solution exists. So solution of AX equals B exists if B lies in the plane spanned by means generated by the two columns of A. by the two columns of A, which simply means if I draw this picture, this is A1, column 1, this is A1, this is some A2, this is some A2, and suppose B is somewhere over here. B is somewhere over here. Obviously, B is outside column space of A. This is the column space of A. This is the column space of A. So B is outside. So assume B is sticking out. B is sticking out of this paper. If B is sticking out of the paper, obviously B is not in the column space. We will not have a solution. But in chapter 3, we'll see. In chapter 3, we'll see that we can always project. We can always project B onto the column space and find a solution. So in chapter 3, what we are going to do, is we are going to project B onto the column space. So let me redraw. So this is A1. So we are going to project B onto the column space, and then so this is the projection, and then we're going to say, since the projection of B, so in chapter 3, so we are going to do projections. So project B onto column space of A. Once we do that, then the projection is in the column space, and then obviously we can always find a solution to Ax is equal to B. So this is the least square solution. You need to wait. So Ax is B is equal to B is solvable even if B is not in the column space, and for that you need to wait until chapter 3. Okay, so this is the column space. So what is column space? Column space is simply the combination of columns. This column space is simply the combination of columns. So combination of columns is the column space of A. So combination of columns is simply the column space is simply the combination of columns of A. Just remember this thing. Just take all linear combinations and you'll get the column space. Ax is equal to B is solving Ax is equal to B is different than solving the homogeneous solution, which is finding the homogeneous solution where B is equal to 0. But that is Ax is equal to 0. So what happens then? So then we have the second space associated with the matrix, which is called the null space. This is actually called the right null space, but right is always dropped, and this is generally called the null space of A. Obviously, A is still m by n. So A is still m by n, and this is called null space of A. So I'm again going to write this fancy n and A just to denote this null space of A. So we need to see, so whenever we want to find the null space of A, we need to solve the homogeneous, we need to find the homogeneous solution. So we need to see what X can attain, what is X? What is X? Need to see what is X when B is 0. So this is simply we are finding the homogeneous solution. So X. So obviously, if A is a non-zero matrix, obviously X is equal to 0 is always a solution. Is always a solution of Ax equal to 0. And obviously we are not interested in this trivial solution. We are interested in the non-trivial solution. So this is the trivial solution, and we are interested in the non-trivial solutions. But there may be infinitely many other solutions. So however there may be infinitely many other solutions, and let's see how to find those solutions. And these solutions are always present when m, when the number of equations, when number of equations, which is m, is less than number of unknowns, is less than the number of unknowns, and the unknowns are the elements of x. So unknowns are the elements of x, and obviously x is n by 1, and number of equations is my, because a is m by n. So null space of A consists of all vectors, x such that Ax equals 0. So to find the null space, to find the column space, we take all the combinations of columns of A to find the null space, and that is what is known as spanning. So if you want to take, you want to know whether the set is spanning a vector space, you take all linear combinations. And to find the null space, and we'll see in a little while, null space also determines the independency of the vectors. So if you want to find the nulls, find whether the vectors are independent or not, you find the null space, or the null space is simply the solution of Ax is equal to set of all the solutions of Ax is equal to 0. Obviously, X has n components, so null space is, it is a subspace. It is a subspace of Rn. Why Rn? Why? Because the number of elements here is n, right? So the number of elements in the vector is n, so obviously it's a subspace of Rn. And these are the solutions to the homogeneous equations, and these are the solutions to homogeneous equations, homogeneous equation, that is for B equals 0, for B equals 0, B is equal to 0. Solutions to homogeneous equations, B equal to 0, form the subspace. All we need to do is find X. Okay, so let's do two examples and you will see the difference. So first, same matrix, 1 5 2 0 4 4 U V equals 0. Okay. So the only solution is U is equal to 0 and V equals 0. And how do we do that? So and just a aside here, whenever these two, so what we are doing is we are doing U times 152 plus V times 044, and we are saying this is 0. So the only solution is when U is equal to 0 and V is equal to 0. This simply means U times column 1 of A plus V times column 2 of A is equal to 0. And we'll see in a little while, probably in the third lecture, we'll see when U is equal to 0, when U is equal to 0 and V is equal to 0 is the only solution, of this equation, this implies A1 is independent of A2. This is written as A1 is independent. This is an inverted pi of A2, or this simply means columns of A are independent. Columns of A are independent. And we can also do it another way. If I write this one and do the reduced row echelon form, so I have 1 5 2 0 4 4, and I do minus 5 row 1 plus row 2, and then I do minus 2 row 1 plus row 2 row 3. Either order doesn't make a difference. So I'll get 1 and 0. Then I'll get 0. Minus 5 plus 5 is 0. This is still 4. Minus 2 plus 2 is 0. This is still 4. And then I do minus row 2 plus row 3. If I do that, I'll get 1, 0, 0, 4, 0, 0. And if I do row 2 by 4, then this 4 goes away and I have 1 over here. So this is a pivot, this is a pivot. So you have two pivots. So you have two pivots. This implies two independent columns or two independent rows. The number of independent columns is equal to the number of independent rows. So this implies number of independent columns is equal to the number of independent rows. So independent rows simply means non-zero rows. Non-zero rows. So there are 1, 2. So there are two non-zero rows. This is a row of all zeros, and there are two independent columns. Why? Because these are columns with pivots. These are columns with pivots. Okay. So what happens if I do this? If I do 1, 5, 2, 0, 4, 4, and I have this matrix B, and then I have 1, 9, 6. So if you are clever enough, you just know, okay, this is A1, or sorry, this is B1. This is B1, first column. This is B2, second column. Obviously, this is B3, but B3 is simply B1 plus B2. So obviously, third column is dependent on the first two. Third column is dependent on the first two. The column space, note the column space of B, note the column space of B is same as the column space of A, because only the first two columns are independent and identical. Okay. However, if I solve X is equal to 0, or maybe I solve Bx equals 0. If I solve Bx is equal to 0, this implies, again, if I do reduce row echelon form, 1, 0, 1. So I am doing minus 5 row 1 plus row 2. Same matrix, so I'm not going to do everything again and again. Minus 2 row 1 plus row 3. So this is 0, this is 4, this is 4, this is 0. Minus 2 plus 2 is 0, 0, 4. Minus 2 plus 6 is 4. And then I do minus row 2 plus row 3, and then I divide by row 2. So this is 1, 0, 1. This is 0, 4, 4. This is 0, minus 4 plus 4, minus 4 plus 4, 0, 0. And then I do row 2 by 4. So this becomes 1 and 1. This becomes 1. This becomes 1. So I have a pivot here. I have a pivot here. So if my x vector, so if, and there is a rule how to write this vector, but you need to wait until the next lecture and then we'll do that. But in the meanwhile, this simply means this is the first equation. So this means so if x is equal to u, v, and w, so this means u plus w equals 0, because we are solving Bs equal to 0. And then second one means v plus w is equal to 0. And obviously w is equal to w. We know w is equal to w. This is obvious. So we say, so these are the pivots. So we say these are pivot variables. These are pivot variables. These are pivot variables. Why? Because this u corresponds to the first column. This v corresponds to the second column. So the pivot variables correspond to the columns with pivots. So pivot variables correspond to columns to columns with pivots, and W is a free variable, Free variable can take on any values, and the free variables determine that whether the solution, how many solutions do we have, and whenever you have a free variable, you will always have infinitely many solutions. So this simply means if I have X over here, and X is U, V, and W, this means if I take out W common, so U is equal to minus W, so this is minus 1. V is equal to minus W, this is minus 1, and W is equal to W, so this is plus 1. So all solutions, all vectors of this, of this form or multiples of this form will always give you Bx is equal to 0, so you have an infinitely many solutions. And in general, actually, if you look at this one, this is exactly this thing with negative sign. Why? Because this is on the left, of the equal to sign, when this goes on the right of the equal to sign. So this is equal to 0 actually over here. So when this goes on to the right of the equal to sign, you'll have a minus over it. So we'll do another example probably in the next lecture, and this will be more clear to you. So this is a line. So this is a line. Through the origin. Obviously, why? Because W can be 0. So W can be anything, can take on any value. So this is a line through origin. Okay. The last article before we stop for today is solve. How do we solve? So solving Ax is equal to B and Ax is equal to 0 are totally two different things. So solving Ax is equal to 0, 0. So let me recap. Ax is equal to 0 and Ax equals B. So for a non-singular matrix A, obviously a non-singular matrix A simply means you have a square matrix, otherwise it doesn't make sense. For a non-singular A, meaning A determinant of A is not equal to 0, or an invertible A, the null space of A contains only 0, and column space of A is the entire space. Why? Because since this is non-singular, this implies your column space, all the columns are independent. Since non-singular implies all columns are independent, since all columns are independent, obviously you'll have, and this is a square matrix, so you'll have the entire space as the column space. So if you have the entire space as the column space, and the number of equations is same as the number of unknowns, since it's non-singular, you have full set of pivots, full set of pivots. So when you have a full set of pivots, so these two together, there are many other things that you can define for a non-singular matrix. So if you have, since you have all columns are independent, all columns will have pivots. Since you have a full set of pivots, there is no free variable. Here. This free variable corresponds to a non-pivot column. So this free variable corresponds to a non-pivot column. Since there are no free variables, obviously the only solution is when X is equal to when the null space contains the origin. And the column space is the entire space. And I'll tell you another check to see what is the dimension. And I don't want to throw names or words over here. What is the dimension? So dimension is the number of vectors that generate the space. So we'll see what is the relationship between the dimensions of the null space and the column space and the other two spaces. Actually, the null space and the column space are not related to each other. It's the column space and the left null space and the null space and the row space that are related to each other. You need to wait until the until lecture 3, and there we'll see what is the relationship between the two. So we need to find what happens. So need to find what happens when null space of A contains more than the origin, contains more than 0, and or the column space of A is less than the entire space, is less than the entire space. So I think the best way is to look at an example and see what happens. So any vector xn in null space of A can be added to any vector, can be added to a particular solution, let's say x of p. X of p is when the right hand side is this is the solution when the right hand side is not 0. So b is not equal to 0. So this implies b is not equal to 0. So we can add it to any particular solution, and what happens? So x equals x of n plus x of p. If I multiply a over a, I multiply a over here, I multiply over here. So I have a times x is equal to a times xn plus a times xp, which is equal to 0 times plus a times xp, because a times xn is the null solution, it lies in the null space. So when column space of A does not contain every B in Rm, so when the column space is not the entire space, that's what it's saying, then we need conditions, on B that make Ax is equal to B solvable. And the analogy is for the scalar case, for the scalar case, 0 times x equals b implies no solution unless b is equal to 0, right? Or this means column space of 1 by 1 zero matrix contains only b is equal to 0. Okay, and what happens when you have 0 x equals 0? Obviously x has, so that implies infinitely many solutions, infinitely many solutions because null space contains all x that is, and we go back to this one. So if you have a null space, which has any vector, which is a vector that is besides 0, if you have xn besides 0, obviously you have infinitely many possible solutions. Why? Because a times xn is equal to 0. This also implies a times c of xn is equal to 0. So you have infinitely many solutions here. So when you add it up here, so you have infinitely many solutions. That's what it's saying. So null space contains all x, that is x equals 0 plus any x. Okay. So let's look at an example, and before we end this lecture today. So this is 1, 2, 1, 2. So there is only one independent column, one independent column, one independent column, and this implies column space of A, column space of A, column space of A is a multiple of this vector 1, 2. This also implies AX, so this is A. So AX is equal to B will have a solution, if B is a multiple of 1, 2, right? Okay, so let me write this equation. So maybe this set implies y plus z equals b1 and 2y plus 2z equals b2. So this implies only solution exists. So implies solution exists if b2 equals 2b1. Otherwise there is no solution, because if you multiply the first equation by 2, you'll get the second equation, and this will be the only, so you'll have a solution only if b2 is equal to 2b1. Okay, so assume b1 is equal to 2 and b2 is equal to 4. Okay, so assume b1 is equal to 2, b2 is equal to 4. So this implies y is equal to z equals 1. This is a solution. Y is equal to z is equal to 1 is a solution. And this or 1, 1 is x of p. So x of p, or x of p, maybe I write it on this side, or x of p is equal to 1, 1. Okay. And if you want to draw this one over here, so this is x, this is y. So this is 1, this is 1, this is a point here. So x is p is equal to 1, 1, or any multiple of xp is a solution. Is this all right? Or any multiple of xp is a solution. Of xp is a solution. Of xp is a solution. And how is that? I'll tell you in a little while. Just give me a minute. Okay, so this one is the line of all solutions. And where is the null solution? So let me find xn. So 1, 1, 2, 2. If I do minus 2 row 1 plus row 2, I'll get 1, 1, 0, 0. This is the pivot variable. So actually, so y is the pivot variable. So this is the pivot variable. Or y is equal to minus z. So my y times z equals z here. This is y plus z. So this implies y plus z equals 0. So y is equal to minus z. So minus 1 here, plus 1 here. So minus 1 plus 1 means, so this is 1, 1. So minus 1 here, plus 1 here means this one. So, and obviously this goes through 0, and this should be parallel. So maybe this one minus 1 plus 1. Okay. So this is, so any multiple of this one will lie along this line, will lie along this line, and this is AXN equals 0, and this is the null space. This is the null space of A. If I combine these two, so let me combine these two. So I have y plus z equals 2, and I have 2y plus 2z equals 4. So I can write this equation. So let me write it over here. So this implies 1, 1, 2, 2, 2, 4. I have minus 2 row 1 plus row 2 minus, so if I do minus 2 row 1 plus row 2, I'll get 1, 1, 2, and I'll get 0, 0, 0. Okay, so same thing. So this is the pivot variable, this is the free variable. So this implies my solution, yz is equal to, so this equation means this is equal to 2, this is 0 over here, plus z, which is the free variable. So this is the free variable, and this is equal to, so this equation is y plus z equals 2, or this implies y is equal to 2 minus z. So y is equal to 2 minus z, and this is equal to z is equal to z. So this simply means z. Well, here, so I'm sorry, z is equal to z. So z is equal to z. So free variable is 1 here, free variable is 0 here. So this is xp actually, and this is xn. So if this point over here is actually 2, 0, and if you use MATLAB, this is what you're going to get. So this simply means this is actually, so your solution actually, so this implies x is actually of this form, 2 minus c and 0 minus c. It's not 2 minus c, sorry, I'm sorry. It's 2 minus c and 0 plus c, 0 plus c. So if c is equal to 1, then you have, this implies this is 2 minus 1, 1, and this is 1, 1, and this is the solution that we said here. So in general, this is the solution of x, sorry, in general, this is the solution of x, this is the solution of x, and this lies along this line. So this is a line of all solutions. So this one is line of all solutions x, which is equal to x of p plus x of n. Okay. So this is the general way of solving the system of equation, which we are going to do in more detail in the following 2 lectures, and I'll tell you how to directly write. So again, we can directly write this 2 from here over here, and this 1, this 1 and 0, sorry, this 1, not this 0. So this 1 is actually reversed over here. So this is the negative of here. Why? Because this is on the left side of the equal to sign. Okay, so this line actually represents the equal to sign. So since this is on the left of the equal to sign, when this goes on the right, you have a minus over here. So let's stop over here, and in the next lecture, we are going to look at the echelon form, and we are going to solve more examples concerning the pivot and the free variables. So if you have any questions, you can email me, or we can discuss more in the lectures on Mondays and Wednesdays. Thank you.